tutto al quadrato, lì, per esempio. Se quello lì è tra meno 2 e 2,
Il quadrato?
li elevi tutti al quadrato e tra
Ah no?
4 e 4, com'è che è la cosa? Fai, non so,
Eh, se levi al quadrato ti viene tutto tra meno...
non si deve poter fare perché fa questa cazzo. Se tu metti tutto al quadrato, qua cosa succede? Per esempio, questo qui deve essere minore di 4. Cioè,
Sì.
ci può ancora fare, deve essere una cosa così.
Il maggiore di 0.
E maggiore di 0 tanto al quadrato, sicuramente esatto, è maggiore di 0. Quindi se levo tutto al quadrato, qua c'ho il quadrato, tanto.
Sì.
Ok, che sembra, non so se serve, un po', magari serve. Qui come faccio a invertire sto ragazzo? Se qua, se qui elevo tutto al quadrato, se questi li elevo al quadrato, no, dopo mi viene un termine qua, o qua, che è una puttanata, è il termine di
Guarda che ti faccio vedere il motivo per cui quelli... Se tu sottrai, fai delle puttanate su quelle cose lì, guarda che cosa simpatica e capisci qua perché il caso con gli L diversi è più problematico. Quando gli L sono uguali, non c'è questo termine, e quindi c'hai una roba con due, una roba con due, e praticamente le intersezioni di questo sono o diagonale o una retta, o diagonale o una retta, fai casi e lo trovi. La differenza degli L mi fa uscire fuori quest'altra coordinata qua, che è una merda. È questa che rompe tutto, che rompe le scale. Il motivo per cui invece funziona. Cioè, quando il sistema è simmetrico nelle L, le intersezioni sono facili, perché sto prendendo solo da due coordinate. Quando gli L sono diversi, le intersezioni sono brutte.
Sì.
Tra l'altro il sistema gode di una simmetria, è ciclico.
Poi proverei a farlo vocale, poi prova a esprimerti. 0 in funzione da qua mi posso scrivere per esempio x0 in funzione di x1, x2 e a.
Sì.
Poi lo caccio qui dentro e qua dopo mi posso scrivere x, cioè qui che lo faccio per tutti, dopo dovrei avere una funzione di solamente a.
Di solamente A, che è dovrebbe essere un grado.
Sì, una merda probabilmente, una
Il
funzione.
problema è che vedi, poi ce n'hai questo per tre volte.
Vabbè, però dopo c'hai tutti e due, dovresti avere x0 una funzione di a, y0 una funzione, scusami, x1
Però pure Y.
una funzione di a e x2 una funzione di a. Per quanto ovvio queste esistono nel mondo.
Ma se non puoi fare il calcolo, poi.
Dopo li metti qui dentro
Esatto.
e dopo c'avrai un polinomio funzione di a che sta tra meno 2 e 2. In qualche modo,
Qualche bound
qualche
strano.
cosa
Tra l'altro,
strana.
la traccia originale è lineare. Questa in realtà è tipo x0 più x1 più x2, meno
Esatto.
questo.
Vabbè, fallo
Uguale.
tutto allora. Esatto. Prima ti trovi questi qua in funzione di a.
Diciamo, io il timore capio, per esempio, no, quando arrivo all'ultimo e trovo,
Sì,
che ne so, x1 in funzione di A,
eh,
quando lo ficco, per esempio, in x2,
sì,
viene una roba bruttissima.
brutta, bruttissima, però intanto fallo per capire com'è. Se qualcosa è, quando lo vedi in faccia, poi ci pensiamo, insomma, vediamo che
Vediamo
cos'è.
se si fa. Perché vedi, eh, immagina che qua ti scrivi 0, qua ti viene un polinomio quadratico in x1, quindi ti viene x2 quadro, x1 quadro, x1. E a questo punto che fai? Ti fai l'adeguazione di secondo grado per x1? Cioè, qua immagina che ti viene a x quadro, x1, x1 quadro.
Sì.
E quindi ti fai il polinomio quadratico in x1 con due...
Ah, x2. x1 e
x1 quadro.
E vabbè, dopo ti esprimi
Ti esprimi?
x1 quadro,
Quindi
lo puoi raccogliere x1 per esempio.
no, perché qua è...
Allora,
no.
quello li porti dall'altra parte.
Esatto, quindi ti scrivi proprio meno b più o meno radice di b quadro meno 4ac proprio.
Sì,
Risolvi
o
le equazioni di secondo grado.
insomma, sì.
In realtà c'è un modo così. Ah, no. E poi le risoluzioni delle equazioni di secondo grado le ficchi. Qua ci avrai un termine x1 alla quarta.
Sì.
E come lo cazzo lo metti? Cioè x1 alla quarta può darti grossi problemi, sbaglio. Ah no, perché poi è lineare questo. Quindi forse...
Non lo so,
Cioè perché
non
vedi,
riesco a farlo.
da qua ti esce fuori x1 in funzione di x2 e a.
Sì,
Qua c'hai x0 sarà una roba tipo x1 quadro, da qua. X1 quadro è funzione di... E tu poi c'hai x0 quadro e x1 è funzione di x2 a sua volta. Cioè, secondo me questo non so se è fattibile. Ci provo, ma ti dico ad occhio che non mi sembra così fattibile. Detto questo,
alla fine otterrai qualcosa,
terribile, ma lo consiglio.
esatto, qualcosa di brutto, molto brutto, però qualcosa
Va bene che sia brutto.
che è, diciamo, corretto, cioè, diciamo,
Formalmente cioè,
corretto, e dopo lo ficchi lì dentro. Certo, effettivamente se è una cosa così brutta è difficile capire, perché dopo tu vuoi sapere se in funzione di meno 2, 2, in funzione di L poi.
esatto,
K lo puoi mettere uguale a 1,
uguale a 1, c'è problema.
e allora toglierlo. Sì, ti dà fastidio. E dopo devi vedere in funzione di L, però
Polinomio, metti caso di sesto ottavo grado, tipo.
sì, è brutta la cosa, però non lo so, lì ci sono dei prodotti, delle somme, non è chiaro quanto complicata sia la formula.
Secondo me, quello che secondo me succede è che nel caso in cui questi sono uguali, ci sono cancellazioni. Quando questi sono diversi, non si cancella una sega. E questa è tutta la cosa. Perché vedi anche qua, immagina che questi sono uguali. Quando tipo sommi e sottrai, qualcosina si leva. Quando sono diversi succede uno smandrappo. No, sicuramente ci provo, ma io sono... Cioè, è possibile
X
che...
quindi è la dimensione di una lunghezza inversa, di una di L la prima. Quindi sì, questi qua ha la stessa dimensione di A,
Sì,
e qua c'hai 3x e 3L effettivamente.
sì.
Quindi questa cosa qui,
X è ordine LM1.
X è un-
A è ordine LM2, in qualche modo. X, esattamente. Sì, sì, sì. A è ordine LM2.
questo però è un po' strano perché X, qua c'hai 3x e 3L e qua c'hai solo 3x. Cioè
No,
qua c'è X
no,
dove
no,
ci
no,
sono,
no, qua
ci sono degli L.
sì, ci sono degli L4 anche strani, quindi tipo L0 però che tutti vanno come... Insomma, sì. Scusami, devi guardare questo. Sì. Tutto funziona. Funziona.
Quindi alla fine qua in teoria potresti avere qualcosa che dipende solamente da una funzione di A ed L.
Sì. Ci dico pure che cosa mi aspetto io sulla
Allora
diagonale.
prova a farlo intanto con gli L uguali.
Tu l'ho già fatto.
E qua cosa ti viene quando sostituisci tutto con gli L uguali?
Viene tutto molto moltipulito e il delta viene tipo 8 su k e l'M2.
Che cos'è?
Quanto nuova che preso.
Sorry. Speaker's here now, so I got to get the setup.
Yeah.
No, no, solo sta 5. Capito? Quindi questo... ok. Io ti dico, tra l'altro, quello che io mi
È fatto
aspetto...
con due L diversi.
No, questo ci provo.
Poi provo a fare due L due anni diversi e vedere se questo metodo di sostituire brutalmente cosa ti dà.
Io mi aspetto che sulla diagonale
Sì.
sia equipartito, cioè sia quant'è? Meno due terzi, meno due terzi, meno due terzi. No, quant'è che deve uscire L a meno 2.
Sì, sì.
Questo è sulla diagonale quello che mi aspetto, mentre le ali dovrebbero darmi una roba tipo L2 a meno 2. Questo è quello che io mi aspetto, però non è detto che sia vero. Io mi aspetto una roba del genere.
Prova a fare un quello inverso per seguire questa cosa qui. Così vediamo se questa strategia qui sostituire totalmente ha qualche senso. Se vedi che i conti sono impossibili, bisogna
La vedi, tra l'altro, con due L diversi, cioè due uguali, uno diverso, no, abbiamo detto due uguali, uno diverso, uno si toglie e uno no. Quindi uno ti dà una soluzione bella, o diagonale o retta. Probabilmente lo ficchi qua, forse qualcosa può funzionare.
però esatto, una volta secondo me il punto brutale lo devi provare.
Sì, sì, no, proverò.
Poi,
Io ero andato qua che è chiaramente il sistema più fancy.
certo.
Però insomma,
Poi se non è possibile,
ricordati che
devi provare.
in tutto questo noi stiamo facendo una cosa e dovremmo farla a ciccia N. Quindi
Però intanto se per esempio il metodo brutale funziona, cioè in qualche modo funziona comunque, magari non perché ti serve la forma esatta di questa FDA, ma è sufficiente avere qualche cosa per avere il bound. Per esempio se è un polinomio di grado massimo, ci sarà un modo per capire dove varia, magari guardando solo il grado massimo del polinomio.
ci sta una roba tipo super algebrica che ti dice
Sì,
se il determinante della matrice è data da
tu è un bound su,
Sì, sì.
cioè, quindi se alla fine il coefficiente di grado massimo, qual è la peggio che come può andare, come può essere la peggio un polinomio? Se questi coefficienti sono limitati, per esempio da 1.
Riuscire a scrivere ha intenzione che la traccia. Quindi magari c'è una qualche, per esempio, che ne so, la derivata di A qualche cosa, cioè, però non sta complicando.
All right, no worries. Yep, I see it.
Good. I will use it in the second half, actually.
Oh, okay, so you don't need the slides right now, right?
For now, like,
Okay, no worries. Whenever you're ready, I'll keep an eye on you. I'll come in and I'll drop the thing for you.
La diagonale fuori vince grosso.
Yeah. Happens. There it is.
Went from upstairs.
Yeah, no worries.
Poi,
No, è uguale. Abbiamo tutte e due.
This is the for the beach. Easy, nice. I think it's a really great piece to start.
Yes. Oh, ça c'est mon stylo. It's last week of May, no?
That's for
Last week of May is 22, the week of 22. And the week of 1st of June. But,
Oh, I had it here on the first, but for some.
but maybe we should check because, you know, I'm not,
Oh, sorry. Thank you.
I am actually overwhelmed with everything we have to do. And sometimes, like I wrote to you yesterday,
Yeah, it's
I
fine.
was confused.
It's here, it's the last week. I don't know why, but on my calendar there was something.
But I'm sorry for the confusion of this 1st of June too. But 1st of June is sunny. Sunny canic. Okay.
So when do we, what times do we do like 4:30 to 5:30 or we need to do it?
Maybe 4 to 5?
Then we'll move to the,
Is it too tight with it for the, it's a little bit tight.
should just move it.
You moved it half an hour?
Yeah.
Or
But then they send the reception tea or something.
yes, it's could be too
Like
tight.
skip the tea. But do they have like special teas for the?
They have a reception. But I don't know if it's before
Yeah,
or after. Maybe we need to check. Huh?
yes.
If we finish 12:30, maybe it's too short. 1 hour and a half more. Shall we start now or it's too?
But then it's too short. Not great to be short.
If it's not at 9, it's too early. It's too early. Maybe
I gotta make it on 9. We can start at 9 and then just.
No, but maybe it's too heavy day, no? We don't want to override.
So, I believe that there is something with the camera, because I think you use all three boards, or do you just use two boards?
I can use two if that's.
Just two?
Yeah.
That would be like pretty easy.
So which
for
one?
recording.
Thank
Yeah,
you.
so I'll mark off like which one.
Thank you.
to use. Yeah. So it's just these two that you can use, and then this one.
But can we change the camera with the button?
You absolutely can, yes. You just have to keep track of it, more or less, like every time he moves. If Catherine, you're willing to do that, you can.
So 3.
Yep.
Is the boards, the 4 boards.
3 is these two.
2 is that.
2 is these two. Yeah.
So you wanna change it?
If it's his two, here's two.
Yeah.
Does it make a difference?
It does, yes.
And this
We
is,
don't see that.
but we don't see the difference.
Can fix it? Do we?
Go ahead and press 3, 2.
This is two, this is three.
Let's do.
Ah, yeah.
Yeah.
So two is this two, and three is this one.
Yeah. So actually, no, 3 is these two, 2 is these two. Yeah. If you're able to keep track, yeah.
Yeah, I do that.
Yeah.
So we are, you start here, Slim, you start on the left.
Sure.
Okay, I tried to.
Thank you.
And your microphone is good.
Yeah.
Thank you.
Okay, so today we'll continue the last theorem, so the proof of the long time existence for fast rotation, and then we'll start like the instability and the justification of the hydrostatic balance. So I'll move to the slides, and I will make the notes available as well as the slides. Okay. Long time. I think last time we defined it, had an equation of the form. Yeah, u plus equal to minus 2 I omega t I1 is I0 minus I is I omega t I minus 1 plus I 2 I omega t I minus 2. We use this formula and the differentiation by parts to define formal limit system, right? Differentiation by parts to define formal resonance system. And the limit system was 2D. Euler. I didn't write the equation on dTV bar. I'm gonna write it now. So put 0, and the second one was transported plus u plus minus 1/2 v bar. Good. So this is what we have done last time. And what we have said, like, so this is a linear system. This is a decoupled system, but the second equation is a linear equation. And it has triple exponential bound. So, and why is that? Because 2D Euler already has double exponential bound, right? And this is a transport fed by Euler. The velocity is given by Euler. So if you do granular, you get another exponential. So this is, you have a triple exponential bound. Okay. Now, elements of the proof of the theorem 3. This for theorem 3. So basically, the same strategy. So we'll define the fluctuation to the limit system. So now we have two components, right? So phi bar to be the barotropic component, and decompose phi plus minus u tilde minus. So we'll define by u plus. Right? And we will choose, so the initial, we will supplement the initial conditions of the limit system by the initial conditions of the original one. So okay. Good. Then we need to rewrite the dynamic for this perturbation. So we have the two components, phi bar. So phi bar satisfies almost perturbation of 2D Euler. Phi bar plus phi bar, the quadratic term, plus exponential 2 pi omega t. So phi 0 q1 plus q2 plus I have a bracket here, minus 2 I omega t p0. So p0 is the z average, right? And q1 minus plus q2 minus. So this is the first equation. And then the second equation. Not going to write it on. But I think the best way to rewrite it is by doing what we have done last time, this differentiation by parts, to introduce the limit system. So something like this, plus E R omega t, another term, plus E minus I omega t, another term, plus 2 omega t equal to 0.
Yes. Bound the solution is in the soluble norm or
Analytic
analytic?
norm, yeah.
Still you have a more bound.
Yeah. So because of this here. right? So we have the double exponential for V bar, but if you do like brutal energy estimate for U plus, you get another exponential, right? Because it's transported by V bar, and V bar has a double exponential.
Not bounded by a double exponential.
Triple.
First one is double.
The first one is double,
Okay.
but for the whole solution is V bar and U plus, right? So the whole solution has two components, right? So the worst is this one. Yeah. Okay. And we can compute these Q plus minus. Minus plus. So we can compute that. Maybe it's useless to do computation here. So now what we want to do is an energy estimate. Okay, so once we have this system, I'm going to do an energy estimate. Okay, so if you do this, so you multiply the first equation by phi bar, the second equation by phi plus minus, then we get and that's called so when we do that, and we will get like 71 terms, basically. Yeah, that we need to estimate. And we will classify these terms in four types. Okay, so classify. So type 1 are those three linear terms, because the nonlinearity itself, we have 2 quadratic, and then we need to multiply, right, by the solution. So we have three linear terms. So these are trilinear terms in phi. Okay. So typical example is so AR exponential tau A phi bar and phi bar AR exponential tau A phi bar. Right? So this is a nonlinear term to which you multiply by this this analytic norm. So to apply the analytic norm, we apply exponential and then AR. Okay, so this is type 1. Type 2. So type 2, these are bilinear in phi, but without derivatives on phi. Okay, without derivatives. Without any derivative in phi.
Is it phi bar? Do you mean phi bar?
Phi or phi bar or phi plus minus. So phi will be, so let's call phi will be phi bar, phi plus minus, and any component of this. So the most important thing is that does not contain any derivative of phi. So an example of this one. So AR E tau A phi bar grad V bar times AR E tau A phi bar. Okay, so the derivative here on the limit system, on the limit solution. Now type 3. These can also be dangerous terms because these are linear in phi. So they need to be treated. We need to have some smallness here. So linear. So linear in phi. So example. And what we observe here at these linear terms, they are always oscillatory. So there is an exponential in front. So this is 2r omega t AR A tau A U plus grad U plus times AR A tau A phi bar or phi. Okay, so this is important to have this exponential, as we will see later. This oscillatory factor. Last type. So these are the trilinear when we have derivative on phi. So sorry, bilinear with the derivative in phi. So typical would be AR A tau A V bar E bar multiplied by AR A tau A phi bar. Okay, so these are basically the four types of terms, and they should be treated separately. Okay, so one thing, I change. So for the first two types, so we'll use nonlinear estimate that I will show at the end of this part. And the most dangerous terms are 3 and 4. I'm going to show you how to treat 3 and 4. So I can write here. So we can use nonlinear estimates here. That I will show. So here, these ones are easier. So use product rules in analytics. So I'll show that. But terms 3 and 4, they need careful treatment. So for term number 3, let me write it here. The idea for term type 3. So let's take this typical term here, this oscillatory term, 2r omega t. And then we have this analytic norm, U plus AR A tau A P bar. So as we did last time, to define the formal limit system, we'll differentiate by parts. So we will write this as 2I omega. And we put the full derivative here. A or A tau A, U plus W plus, A or A tau A, E bar, right? So this is the first term, minus 1 over 2I omega, EI 2I omega T, dt of the same bracket, right? Okay. So time plus this small factor times a full derivative. Okay. Now let's try to estimate. So this guy here, the time derivative, when the time derivative hits here, so that will generate more nonlinear terms, right? But the good thing is that this is given. This is the limit system, right? So this is something we know. So the second term, this second term here. So the second term can be bounded by, or estimated by 1 over omega. You have this 1 over omega factor, and then time derivative hits the radius of analyticity, then you will get tau dot. And then you will have AR plus 1, E tau A, U plus at plus AR E tau A, E bar. Right? So this is the first term when the time derivative hits the radius of analyticity, and then you have other terms. So AR E tau A dt of this quadratic times AR E tau A P bar. That's the other term, the last term. AR tau A and then U plus add U plus and then AR E tau A ET phi bar, right? Probably need to put absolute values here. So you can say that this is less than some terms I1 plus I2 plus I3. And again, using nonlinear estimates, so we will talk about this. A nonlinear estimate, what you get is some constant depend on omega squared plus CR AR plus 2 E tau A U plus. So this really does not matter, right? Because we can put as many derivatives here because this is something we know, right? And then so at the end of the day, so term 3, type 3 terms. They give us, we can rewrite them as dt, some nonlinear function. This is the term that I didn't do anything yet, just full time derivative, plus some remainder that can be well controlled, like this one.
when
And
you
how
put the,
how
when
do you bound the type one?
Uh,
How do you absorb the derivatives of you have also one derivative of phi?
yeah, but we are working on the analytic space. So you have the tau dot, right? That you can absorb.
And
So the frame the
and what is do not affect the time of existence?
sorry.
I mean, okay.
Yeah, I mean really there is no problem
Now,
later on. Yeah,
okay.
yeah, later on. I didn't finish. So just said like type 3. So we need to appear the limit equation, and then we appear the limit equation by this differentiation by part. So we have dtn plus something which is well estimated. So we still have to estimate this one, right? We still have to estimate this one.
what do you do with when you have the DDT on phi bar?
You replace by the equation.
Or replaced by the
Yeah,
equation?
yeah. So you'll get more powers, more non-linearities. Okay, so this is for type 3. So you can estimate them like this with R. So let me finish. Good thing is that R can be estimated some constant. Can put here U plus minus, can put V bar in R plus 2. This is X tau R plus 2. So you can put really regularity here to some power 4 plus 1 times the norm of the solution, phi bar phi plus minus. So here we don't want to lose. Okay. So this is the type of estimate that we will have on R, but still we need to treat the N. Now, what is good about N, so remember when we do energy estimates, so we have d by dt of the norm of our solution is less than dtn plus this estimate on R. So we need to integrate. We need to see how dtn is estimated. So this is equal to what? This is equal to n of t minus n of 0. But n of 0 is 0 because our initial condition is 0, right? So phi bar plus minus. So this is 0. So this is n of t. And that can be estimated since we have 1 over omega, some constant. So norm of V bar U plus minus X tau R plus 1 times norm of our solution X tau R. Yes.
How do you get the bound from the vendor for this I1 hydride?
I mean, you use nonlinear estimates again and Young's inequality. Yeah.
And like
I'm skipping a lot of details here. Yes. Yeah. I'll show you the type of nonlinear estimates right now. But yeah, there is some work here. But please believe me that this is correct. Okay. Yeah, if you remember, yeah, exactly. So, yeah. Yeah. Okay. Now, the fourth term. So this is type 4 now. So type 4, we have like 23 terms here. But here, so there are, yeah, I think this is 23. This is type 314. And then first one 19, second one 15. So if you add them up, you get 71. So, but the thing here is that we have many cancellations. Okay, I don't know how to explain that, but so many cancellation, algebraic cancellation, not algebraic, but cancellations. Yeah. So, for example, give you two terms. So V bar grad. If you do this guy, we do integration by parts and so on. Commutations and so on. So this V plus V minus plus V bar. So here you do the commutation with AR. V minus AR. Now A V plus. So this is 0 because the divergence of V bar is 0. So this is one of the cancellation, but there are more other complicated cancellations. So now if we summarize all the, or if we sum up all the terms, summing up. And setting, let's set F tau R to be same as before, the norm of the solution. So AR, tau A. So if we set that, including the L2 norm, then we have d by dt of F tau R is less than tau dot plus some constant that depend on R, F tau R 1/2 plus tau times function that is double exponential plus A2 over omega naught. Then, so here we have the loss plus K2 tilde F tau R plus sorry, so this is plus K2 tilde times F tau, yeah, plus K2 tilde over omega naught plus DTN. So we still have that DTN. And then we use exactly the same idea, the one that I explained it last time. The same idea, so we impose, or we choose the radius of analyticity to be non-increasing, so that the term vanishes or can be omitted for free. And then for that, then we use that to get an a priori estimate of f tau r, and then we replace it in the differential equation. So exactly the same steps. So choose tau dot plus CR into tilde equal to 0. Then that will give us d by dt of f tau r is less than k2 tilde f tau r plus explicit function plus dtf, right? So this is a differential inequality on f, right? The size of the solution that we can solve, right? So solve. But remember that when we integrate, so when you solve for dtf, you integrate, you get n of t, and then we have n in terms of the solution itself, and then you can bootstrap. Okay. So the last thing, yes.
There are a simple way to solve the equation.
Which one? This one?
F depends on tau.
This one?
Yeah.
Yeah, I mean, so first you impose that it's non-increasing, right?
Yeah.
And then you get a bound on f, and then you come back and you solve for this. So I think the easiest way is what really I explained last time, when we had much simpler situation, right? When we had much simpler situation, have it here. Yeah, so last time we had something like this. D by dt is less than 4 plus this dissipation here. Tau dot. So tau dot plus CR f1/2 tau r plus 1, right? This is what we got last time. F tau plus 1/2, right? So what we have done, we said, okay, let's take this as non-positive, right? Then we get a bound on f tau r, a bound that depends only on the initial condition. And then we plug again. Now we have a bound on f. So we plug it again. So everything now depends only on the initial condition. And you can solve this differential equation to be 0. So that's exactly the same strategy that we keep repeating. But so here you see the effects of the fast rotation, because you have these small parameters here. So what I'm saying, suppose you can choose tau. so that this is non-positive. Then you can immediately get rid of that, and then you can solve this differential inequality. You can solve it because everything else is explicit. This is explicit. This K2, it's double exponential function.
Why the other terms?
Sorry?
So you have other terms. Yeah.
Here you mean?
The last three.
Yeah, this one is coming from
Yeah.
terms of.
But why you don't? For example, you can bound that tau r and that.
Yeah, this one.
For example, the first one.
This one.
Yeah.
Yeah, I mean, this is you will integrating factor, right? So this you will have it as an integrating factor here, right? This term and this term, so we will get d by dt exponential K2 tilde times f tau is less than something, right? We put it as an integrating factor, this one.
Yeah, but my question is why you don't include it in the first?
In which one? This one?
Yeah.
No, this is with the loss. Here you have a more regularity, right?
But maybe because
Yeah, but
it's
you can
one,
bound.
it contains 1 over omega. Because it contains 1 over omega, so it makes solution smaller. This term will contribute with being very small if omega is large enough.
I mean, you want to estimate this by in here? Sure. Okay. Yeah. Yeah, you don't have a ground wall. Yeah, you're right. Ground wall. Yeah, but I mean, so basically you can solve. You can solve explicitly because now this is an integrating factor. Everything is under control. But the idea is really the following: you have an estimate like this, then you choose your radius of analyticity. You assume that you can choose your radius of analyticity so that this is non-increasing, right? Non-positive. Then immediately you get a bound, an a priori bound on F, right? Which you, when you substitute back in the radius of analyticity, you can basically solve.
Sorry, maybe confused about why you don't use tau to englobe all the steps in this.
I mean, we are solving for two things, right? We are solving for the time and for tau. But two things, right?
Yeah. How do you decide
yeah, I mean, this is exactly how you decide. You choose your dissipation to the coefficient of the in front of the dissipation to be non-positive, right? And then that gives you an a priori bound on your solution. Then you go back to the radius of analyticity and you really can solve it almost explicitly. And I think the best example to understand that is what we have done in the last time, because you don't have all these complications coming from fast rotation or smallness.
An optimal way of.
There is what, sorry?
Yeah, an optimal way of.
What do you mean optimal?
I mean, in the sense that, well, I guess like this related to his question, maybe is there a way to like get this like without using this strategy?
Using what, sorry?
This strategy. So basically, because you're just saying that, I mean, you just wanted non-negativeness on this factor, and then you just throw it out, and then you solve, and then you come back. So maybe it's way too.
Maybe, yeah, maybe. Yeah. Yeah, I don't know.
If you have a simple quasi-linear problem and you want to do a Cauchy-Kovalevsky activity, you choose the size of the band of analyticity, essentially linear. And when it touches 0, it's at the end of your theorem, finite band. But here it's a little bit more complicated. So you have to choose the size of the analyticity band, not
to shrink to 0, not to shrink to 0 fast.
Not that fast.
Yeah, exactly.
More complicated. It's more subtle.
Yeah, it's much more slower time.
So you can have very long time.
Yeah.
Can also optimize, but it's irrelevant.
No, absolutely. Yeah, I mean,
Upper bound more by the time.
I mean, I'm not saying like, I'm not claiming like this is, yeah, I'm definitely not claiming like this is really optimal in terms of sharpness, even if the regularity, we really didn't want to investigate that. But
you really want a very long time.
yeah, exactly. So, I mean, we wanted to see the effect of the rotation, fast rotation. Because, yeah.
This is the rate.
Yeah. Especially if you know that your solution does not exist for all time. This is the difference between Euler and the primitive equation. This is the big difference. Euler, it's hypothetical. You don't know that solutions are blow up in finite time for smooth solutions, right? But you see you see the effect of the rotation. You see the effect of the rotation. But here you see the effect of the rotation when you know that solutions are not global in time. Yeah. Okay. So the last thing. So the last thing is. So the nonlinear estimates. I'll just. So we have two types. So the first one, we call it lemma 0. So this is exactly like for Sobolev, but in the analytic framework, where if your Sobolev index is high enough, then it's an algebra. So this is an algebra, right? It's like for Sobolev, but now you work with analytic norms. Now, if you estimate the non-homogeneous, the homogeneous norm, if you estimate, then you will have the average of your solution. Okay. Sorry?
On the left is out.
HR.
No, in the.
This one L2, yeah. This one is L2. This is the Fourier coefficient, the zero Fourier coefficient, yeah. Times G0. And if you remember, so for us, we did work on if you remember, for us, we assumed that the initial condition has a zero mean value, right? And that propagated, right? And we showed that the mean value of the solution So it propagates in time. So if you assume it's zero beginning, then it will stay zero for time. So this is the first type of nonlinear estimate. The second type is to estimate the trilinear terms. For lemma 1 trilinear. So we have three types basically. F G or eta A H, right? So this is the one that we use to do the energy estimate. And we want to distribute this derivative to the other terms. X tau R plus X0 norm of G X tau R plus 1/2 norm of H X tau R plus 1/2. So you distribute one derivative into these two terms plus norm of G X tau R.
You have this one divided.
Sorry?
But you have 1/2.
You distribute. So you have this one derivative you distribute. Yeah, distribute it half here. So this is A, this is B. A R A tau A. Now we have the second type of terms of nonlinearities is divergence F times G. A R A tau A H.
Sorry, I don't get the round parenthesis on the bottom line.
Sorry?
There is that round parenthesis on the bottom line where I think it's open.
Shouldn't be that. Yeah. Yeah, it's the constant CR that in front of everything. Sorry. You're right. Okay. So this last one, the second one, constant CR G X tau R plus G0 norm of F X tau R plus 1/2 times norm of H X tau R plus 1/2 plus norm of G X tau R plus 1/2 X tau R.
In this class, if you have on H, then you have plus 1/2.
No, I think you don't have here. Yeah, you can estimate this one. So this is when R is large enough. This is when R bigger than 2. I should have said, so this is when R bigger than 2. Yeah. And F bar Go to 0.
Okay, so if you say one derivative of the h for the first one, you get the 1/2 on h, 1/2 on b, because we have to get the same thing on f and h as well.
One second. So, sorry. Yeah. I mean, you gain here. You gain. So this is R. The second one is R bigger than 2. And so this is the second one. The last one. We have 3 types of nonlinearities, right? So one is like to the Euler, and the other one is coming from the V tilde. So this last one, AR A tau A, DZ inverse nabla F times DZG AR A tau A in H. So this is the last type of nonlinearities. This is the most painful one, is this one. CR norm of F X tau R norm of G tau R plus 1/2. Right. So here you have the loss of derivative plus norm of G X tau R plus 1/2 X tau R. So this is when R bigger than 2 and tau can be 0 and F bar is 0. So for the proof, it's Fourier analysis. I mean, you can rewrite each term and then yes.
Oh, orienting, but you mentioned the cancellation of certain terms.
Yeah.
But they don't look so different from the others. Was it important that they cancel it, or?
Yeah, for the other part, yes, it is important that they cancel. Yeah.
So they're not handled.
No, not handled here. Yeah. It's really important that they cancel. Yeah, absolutely.
Why?
I don't know.
But
That's a good question.
when you show that thought, these are the terms that cancel for standard energies. So you have to go without calculation. You look at the floor, right? I mean, it's about
It was coupled, right? It was coupled. Not just to the Euler. It was coupled.
But it's still coupled coming from something that originally had energies.
Yeah.
Or some echo of the.
This is the same, I think so, yes.
Okay, another question? Do you know how to? I want to use this slide. This one? Video?
Maybe for sure here.
This one?
No,
This one?
no, there's no doubt. I think it's the volume. Oh, yes.
Yeah. Okay. Thank you.
There are people think,
Then I'll send it to Zoom once you load it.
It's already loaded.
Oh, okay, okay.
But do you know how to?
We should send it to Zoom.
share. Yes.
Sure.
Is this one?
Yeah, that's one.
Maybe automatically.
Yeah, very good.
How to turn the projector on? That's
Maybe
that's
here.
that's
Yeah.
I should be
Off.
turn on.
Maybe video. On.
Or maybe there's here
The on there.
This one.
Yeah, I think so. Let's see. That's something.
It's working there.
Blinking. We will. Maybe from PC one.
PC, yeah. I think it should be PC.
Otherwise, we'll ask.
Oh, maybe it's this object.
No idea.
I try. Maybe I
Turn it on. Turn it on.
everything now. It's good.
Yeah, because it's blinking. Maybe it's not going to.
Oh yes. Yeah,
Good.
turned on.
Lovely.
Yes.
Great.
Okay, so now we move to the third part of this course. So what we have seen so far is the well-posedness in the set of analytic functions, right? And how to use some more structure on the equation in order to get longer time existence. So now we want to see the other side of this equations. So two things, why we have worked in the space of analytic functions. In the first lecture, I explained it like that was due to the instabilities that appear in the system. So this is the purpose of this part of the course, is to study these instabilities, which will somehow dictate the natural framework to study well-posedness. So this is a nice paper that I've read. It's quite recent by Bianchini, Roberta, Micheli, Cotti, and Lucas. That has appeared like a few months ago, at the end of 2025. Okay, so shall I use this one?
Yeah.
Can
I just go?
just remove?
Yes, remove.
No?
Maybe you have to turn it on in one. There is an on-off somewhere on the here, like.
Yeah.
Yes.
Work?
What do you? Oh. Okay. No, it works.
The black. Oh, yeah.
It works, but it not turn the slides.
You know, so you have to remove, just close the thing with PDF.
Yeah.
Yeah, and then, yes, and then remove this one. Let's try it again.
I did a direction.
This works, and it's really something, but usually
Does
there's
it work with your computer? Okay.
Yes,
So then this means that there's something wrong. So
I
that's not
can.
fine.
yeah, this we're calling this way, I think.
I can do it manually.
Yeah. It's working.
Okay.
Yeah, because it's the other direction. You have to run both directions.
Ah,
It's counterintuitive.
It's working, right? So
now it's working. Wow.
No, yeah.
you can use this thing to go back. Then you send it.
Okay.
Set the wrong value.
Okay, good. Okay, so sorry about that. So I'll recall what is the Euler-Boussinesq and the hydrostatic balance approximation that led to the hydrostatic Euler. And then I will recall very classical criteria about stability of shear flows that goes back to the 60s, I think, by Howard. And then I'll explain what are the difficulties for this hydrostatic Euler in terms of stability and the justification of the hydrostatic balance. And then, so the last the part which is crucial here, it's about linear instability, how to exhibit an example of shear flow or solutions that has a growing mode. And then how to upgrade this linear instability to nonlinear one. So you need more structure on the spectrum. That will be the last part. Okay, so again, so now I think we are familiar with this Euler-Boussinesq equations. So the first equation, the first two equations are the moment equations, right? And then we take stratified flow, meaning like either we have a density here, so the velocity, we have a density that is transported by the velocity, or by temperature, if you think of the atmosphere. And then the physical boundary condition is that the vertical velocity at the top and the bottom is zero, right? And let's assume like our domain is really the torus cross minus 1, 1. So you are taking like a three-dimensional flow that does not depend on the y direction, basically. Okay? And here epsilon is coming from the thin domain, right? When we work with the atmospheric or geophysical flows, then these are thin domains, and you can rescale and get this epsilon square in front of the vertical acceleration. Okay, now formally speaking, if you take the limit epsilon goes to 0, it gives us this hydrostatic Euler-Boussinesq equation, right? And if you assume that the density or the temperature was constant, this is what we call like isothermal case, then you get what is called hydrostatic Euler equations, which is just that equation plus the temperature gradient in the z direction to be 0. Okay, so two main goals here in that nice paper is to see whether the hydrostatic approximation is valid or not, right? And if you remember in the first lecture, what I said is whenever you have a horizontal viscosity, then this was justified, right, by many nice works and so on. But here the thing is that viscosity is not here, okay? And then also we need to understand what does it mean, like the limit, right? We really need to define what does it mean the limit is well justified or not well justified. And in this paper, so the thing is they will relate it to stability question. Okay. And the second type of aims is to investigate the limiting system, this one, right? Not in the analytic space, because we have seen in the analytic space it's well posed, but in the Sobolev, what happens? Is it well posed or not? And if not, what's going on? So these are the two aims. So today, let me try to refresh, because this is a course, so let's try to refresh this Miles-Howard criterion that is due to the 60s, basically. So you consider a shear flow, right? So the shear flow, you have a density here, and then you have the velocity. The vertical velocity depends only on the z direction. And you can adjust the pressure, so this is a true solution to our system. Okay, so this is called the shear flow. And it's a solution no matter what epsilon is. If epsilon is 0 or non-zero, then this is always a solution. You can check that. And there is this nice result, a sufficient condition for stability, if your solution satisfies this condition, then it can be spectrally stable. So I want to show you this one before going to the more sophisticated stuff that that paper talked about. Okay, so let me, I've done the computation on slightly different thing because I was lazy. But you can, it's exactly the same criteria for the Euler-Boussinesq equations. So let's consider like the 2D Euler with coupled with the density here. And then you have the buoyancy force here. And you want to study the stability of this shear flow. Okay, so basic analysis. So we take a perturbation, and you take a perturbation in the density. You write it this way. Okay, you decide to write it this way, and you look for an ansatz that has this shape. Okay, and as long as the imaginary part of C is non-zero, then that will tell us that there is instability, right? Because we will have time growth. Okay, so you take this, and as you plug it into the equation, then what you get is this quite famous differential equation, 9. And this one denotes the derivative. So let's call beta to be this ratio. Okay. And let's assume we have non-slip boundary conditions. So we have a layer between y1 and y2. So from the definition of eta, so as I mentioned, so the instability is as long as the imaginary part is non-zero. Okay. So k is a wave number. It can be positive or negative. So, okay. Then you can change the unknown W to be the shear flow, your shear flow minus this frequency C that you are looking for, right? And since we are looking for imaginary part of C non-zero, then the imaginary part of W should be non-zero. And then you can define the root, the complex root. Okay, so you can change, instead of looking to capital F, now you look for capital G, and G now it will solve this differential equation. So what we are looking for here is non-trivial solution G and the C, right? Let's see. So Miles-Howard trick is once you have this differential equation, you multiply by the conjugate and then you integrate. So when you do so, you get this nice identity here. Okay, and the imaginary of W is nothing but the imaginary of C. And that's what we want to have non-zero. So now, if you look to this nice identity, this has a sign, this has a sign, and this will be zero unless this function changes, has a zero, right? And that's exactly the stability condition that. So it's a very classical, nice argument. But now let's go back to the questions that we want to prove. So the paper proves two things. Okay, so the first thing is the validity of the hydrostatic limit. It's not correct. It's not valid, the hydrostatic approximation. And they do so by constructing like explicit shear flow. It's stratified. Stratified means that the density is non-trivial. It's not constant. And this stratified flow, it's, as I mentioned, so it's a solution to the epsilon Euler equation with epsilon can be 0. And then you reconstruct an initial data It's a family of initial data that is arbitrarily close to this shear flow for any k, so as close as you want. But they construct a sequence of times going to 0, right? So that if you take the corresponding solutions and you measure them in this L2 norm here, then it's bigger than any prescribed constant that you have fixed at the beginning. Okay, so this means, so this is the meaning of the, like the limit, it's not correct. Okay, then the second, then the second type of result is, now you take the limiting system, which is hydrostatic Euler equation, and you want to see if you have well-posedness in Sobolev. Okay, so the second, so the second result is that this is not true. So they can construct Sobolev initial data for which the flow map, it's not Holder continuous. Okay, so I mean there is no standard way of ill-posedness, right? There is no general for all the I mean there is no general definition for all the equations. Okay, if you take the heat equation, for instance, for me ill-posedness is when you lose uniqueness, right? When you lose uniqueness. But for dispersive PDEs, for instance, ill-posedness is in this sense, basically. So if you take the flow map, then it cannot be Hodder continuous, for instance. Okay, so this is the notion of ill-posedness that will be adapted for this type of equations.
Why is that?
Sorry?
Why is that good notion of
That's a good question. That's a good question. Because I mean, so people say, okay, you cannot construct solution via fixed point arguments using for these equations. For these equations, for these initial data. Right?
This is defined according to Hadamard.
Yeah,
You have the three conditions that you have.
Sure.
Existing uniqueness, and if any of those are violated for some equation, then you know the application is not true.
But for
Hadamard is just continuous.
Continuous, yeah, continuous, just continuous. I mean, but still, people they call it ill-posed in the sense of Hadamard.
Does it just mean that it's a linear equation?
It does. It yeah.
For Euler, so
Yeah,
Euler is,
yeah, basically.
but then by this definition, you could say that Euler is opposed.
Yeah.
Always. Because Euler cannot be Euler. And it's not it, just for Euler, right?
For quasi-linear, yeah, for quasi-linear.
Yeah.
Yeah. But you have other types of equations also. You have other types of equations where you have this property, not quasi-linear, even.
Yeah, that's fine to put.
Yeah.
But is this quasi-linear or not?
Yeah, I mean, if we,
it's quasi-linear.
yeah,
That's what it means.
ill-posed.
No, this is what it means to be quasi-linear.
Yeah, absolutely, yeah, I agree.
It's just
I agree.
you don't have
Yeah, I agree.
different dependence.
Yeah.
Yeah, even for Euler, right? I think.
Yeah.
Just dependence on the data.
Yeah, I agree. I think, yeah. we should change the definition to quasi-linear of being quasi-linear. Yeah, I agree. I mean, the best ill-posedness result that I really like is for the heat equation when you do the uniqueness. That's a true. This is Ni and Sachs results, and Elie de Terranio and myself also. I did work in the 2D case. I think that one is really a true ill-posedness result because you lose uniqueness. You can construct initial data that has two different solutions. But okay, this is weak, I think. But that's what it is, even for some dispersive equations like NLS, and that's the definition basically. Okay, I'll finish with this. So the ill-posedness result will mainly come from a linear instability feature, as we will see next time. However, this is, I mean, for other equations, you can have different mechanisms. Right? If you take dispersive equations, this is the ill-posedness mechanism is not linear. You basically construct like other types of solutions, like ODE solutions that oscillate quite fast, and then they will be apart. But for this type of equation, the instability here, it's really coming from the instability of the linearized problem. And the shear flow is kind of explicit, and it's given by this family of parameters alpha here. And you can see when alpha is 1, then you get isothermal unstable flow. Okay, so the density becomes 0 or constant in this case. Okay, so I'll probably stop here, and then next time, so we'll do the instability, the linear, and then a nonlinear, and the last lecture would be the blow up. So the blow up will be on the blackboard. Yes, thank you. See you.
Is Han Kwan and Yen.
Yeah,
My student, but yeah, but not so much to do with me, but also had to do with a postdoc of mine, Texier. There's a paper by Yen, Texier and Lerner. Yeah, instability results of a different kind. I'm just wondering, this particular framework, what is it that, what's the key? They have a continuous spectra of what they're trying to find nonlinear instability, right? This thing.
Yeah. They try to find the nonlinear instability and also the like a biggest eigenvalue. This is very important.
But it's still not isolated, this biggest eigenvalue. Or is it, they have to find a biggest eigenvalue that is isolated, or?
It's not clear to me, to be honest. But it's a really important step, like there is this dominant eigenvalue. It's otherwise they cannot. So they do this in a box, large box limit. So I'll explain that.
Yeah. Looking forward to it.
Yeah. No. This is the essential point. This is exactly this. So that's what I like about this result is they do this large limit box in order to guarantee like this dominant eigenvalue is a dominant.
It is the hardest part to show boundedness of spectrum. That's part of it, right? To show it doesn't grow without a bound. And then it will dominate the others.
Yeah, it will dominate. Yeah. I think for that part they use this large box that I should talk.
Nice.
Yeah.
Very funny when my student was looking for his first job. He applied to IU. Maybe it wasn't his postdoc, but somehow we had the letter. So I had to see the letter of the guy writing. It's much broader than his advisor. But it was true. Like 2 years after it was true. So wait, okay, that's true. That's very. But yeah, he's really good.
Yeah.
Very prolific.
Yeah. I like he's weak too. Yeah. For some,
honest, he hasn't leave it. He has to.
No. I think
is he moving?
No. He's not moving. Like he has like a contract 3 months.
Oh,
I spent 3 months there
interesting. Yeah,
Yeah.
I mean, he does a lot for,
for his.
yeah, yeah.
Yes.
He did summer schools and things, so I guess it became formal.
I think so. I think so. The guy who spent on, I think he hired 2 or 3 of them. They told them, no, you need to come back 3 months.
So I gave a course at one of those summer schools quite a while ago in Vietnam. This is really nice. It's very, very, very interesting, surprising in many ways. But kind of a highlight for me was the director of the Vietnamese Math Society. He dates back to the Cold War, the Vietnamese War, like those periods. This guy was really tough. And he was saying, and he had in there Tuan and a couple, like 3 other Hung Tuan, some guys, really good young guys in the U.S. Comment. It seems like a pretty non-negotiable.
Non-negotiable, yeah.
Could have come back. And now it happened.
Wow.
Would you feel like, yeah,
Well, I think that's nice.
you know? No, I yeah, I think you have to be pretty tough to survive so many political changes.
Yeah.
And still be everything and successfully. Like,
Yeah.
how many good?
When was that? When you?
That was, I think, like 2000, I feel like 2015.
Okay, before COVID.
Yeah, yeah. It was really, really, it was very beautiful. It's really, really hot. in the summer, for sure.
Summertime, yeah, of course.
There are lots of scooters. Oh man, it's great. There's scooters in the street. Really amazing.
Oh, yeah.
Yeah, but
Maybe now it changed a lot, I think.
I bet it has.
Yeah.
Yes,